Welcome to the lectures on modern digital communication techniques. So, in the previous lecture, we were discussing about the performance of orthogonal signals, emery orthogonal signals, and what we found is an interesting result which is in contrast to the situation of emery PAM, is that as we increase the constellation size, we found that the required EB by N naught decreases, or we could say that given a particular PB, the EB by N naught decreases, or given a particular EB by N naught, the PB decreases, which can be visible from this particular figure that we have drawn. Is that as we increase the constellation size, if we keep the constant PB and we want to increase m from m equals to 2 to 4 to 64, the required EB by N naught decreases, right. On the other hand, if we have to view it in a different way, that I want to keep the constant EB by N naught and I keep increasing m from m equals to 2 to m equals to 4 to m equals to 64, what we find is that PB keeps on decreasing. So, the question that remains with us is, if we keep on increasing m indefinitely, then what is the impact on EB by N naught, that means on this side, or what is the impact on probability of error. So, technically we could say that as we keep increasing m, we could in the limit almost make PB vanish, right. So, if that happens, we should also be able to travel on this direction. So, what is the EB by N naught that we reach is the other important question. To partially answer that, what we could do is, let us write down for orthogonal signals the signal structure as we have here. So, for this signal structure, we know that the distance between any two constellations, the Euclidean distance, is root over 2 e. That is, it is the constant distance, and this is what we have been trying to explain in the previous lecture, that all the constellations are equidistant from each other. So, for 2 dimensions you can easily visualize this. That means, for 2 dimensions you could easily visualize that this is one constellation point, this is another constellation points. In 3 dimension, if this is x, y and z plane, then possibly we could have it this way, but beyond that it is left to our imagination. So, if we imagine them to be some orthogonal dimensions, a particular signal is equidistant from all others. If we take any other signal, that is equidistant from all others. That means, the distance between the constellations is the same. That means, that is the minimum distance of the constellation. So, at this point we would like to recall the discussion we had in the lecture before the previous one. Is we explained that why the minimum distance of constellation plays a very important role in, or plays a dominant role in, the error probability expressions, right. So, taking that and we did write the expression in terms of d mean squared, that is the distance between the two constellation points, the minimum distance. So, here what we find is that since distance between the constellation points remain the same, therefore, the probability of error should not be affected, that is the premise. So, for k increasing, as we increase k, as we increase m, d remains constant, right. This is the basic thing that we have, whereas the Es is the signal energy, that is k times Eb, because it is a signal energy, there are k bits per symbol, and Eb is the energy per bit. So, if there are k bits, k multiplied energy per bit is the energy per symbol, where there are k bits per symbol. Where there are k bits per symbol. So, now some things could be a bit clear, in the sense that as we increase k, we are actually increasing Es. So, if we are increasing, so that means if we keep Eb constant, as we increase k, we are actually increasing Es. So, if Es increases, that would mean D increases. So, if D increases, that means probability of error decreases. So, that is a straightforward thing that we have. So, if I am going to increase k by keeping EB constant, that means I am increasing the total energy, because ES is equal to k times EB. Now, if ES increases, what we have is dkm is root over 2 ES. So, this increases, the distance increases. If distance increases, probability of error decreases, or you get a better probability of error result. So, that is what is clearly visible over here, right. For a constant EB, as we increase m, that means as we increase k, the probability of error decreases, simply because distance between constellations increase. Well, the same discussion can be argued in a slightly variant way, almost meaning the same thing. So, for the constant d min, P m is unchanged, we know. So, as k is increased, right, bits are increased. So, going by this, if k increases while this is kept constant, that means E b must decrease, right. So, in other words, it is saying that if I am increasing the constellation size while keeping the signal energy constant, that means while keeping d constant, that means while keeping unchanged P b, then your E b requirement decreases. So, that is the other view that we have. So, if we have E s as constant, that means if we have distance is constant, because if E is constant, D is constant, right. If E is constant, D is constant, it would mean that probability of error is unchanged, that means we are talking of this line. So, if that happens, as k increases, if this is constant, then this must decrease. So, as k increases, that means as m increases from m equals to 2 to m equals to 4 to m equals to 64, k equals to 1, k equals to 2, k equals to 6, what we clearly find is that as we keep this constant, we traverse this line, because P b constant, D constant, E s constant. So, k increases along this direction, So, therefore, what we have is E b decreasing, this is E b by n naught is constant. So, this is constant. So, gamma b decreasing, E b decreasing means gamma b decreasing. So, both the things could be explained by looking at the expression and arguing in terms of the minimum distance of the constellation points from each other. So, this is qualitatively argued, but we are still left to find out that what would be the minimum E b by n naught that we require. To proceed on that, one could resort to the union bound on probability of error. So, that is what we are going to look at in this part. So, what we could do is we could calculate the probability of error for the binary orthogonal signals, right. So, we did not give the result, that could be used by what we have done, or it is not very difficult. It is basically using the correlations, that is C of R S 1 and C of R S 2. So, if S 1 is sent, what is the probability that outcome C R S 2 is greater than probability outcome of the correlator C R S 1. That is what we have done, and for 2 it is possible, for more it becomes a bit cumbersome, and it is equal for both the situations. So, the result that you obtain if you do that is q function of root over E b by n naught. So, just a reminder, for binary PAM it is q of root over 2 E b by n naught, just for your comparison sake. Thereafter things change. Now, we could view the detector for m orthogonal signals as that which makes m minus 1 binary decisions between the correlator output C R S 1 and the other m minus 1. So, what do you mean to say? We select C R, the output of the correlator of C R with S 1 compared to that with C R of S 2. So, that is one comparison. We could again compare C R S 1 with another, we could again compare C R S 1 with another, and so on and so forth. So, we could compare with all of these correlator outcomes. Then the probability of error is upper bounded by the union bound. So, what it means is that union bound of the m minus 1 events, right. So, if E I represents the event that the correlator output of R with S I is greater than correlator output of R with S1 for I not equal to 1. That means, correlator output S2 is greater than this, S3 is greater than this, S4. So, any particular is the event EI. So, C of R S1, that means, if fifth correlator output is greater than the first correlator output, that is the event E5, and so on and so forth. Then probability of error is the probability of the union of all these events, right. That is true, because it is orthogonal signal. So, you have to take the probability that the second is greater than the first, the third, fourth and fifth and so on. So, you add up all these probabilities. So, this probability, so we calculate the probability that the union of these events, and this is bounded by less. So, this is less than or equal to sum of these probabilities, right. So, this result can be derived. So, this is limited by the sum of these probabilities, right. So, of all these events, probability of all these events, individual events, that is the worst case scenario, right. So, the probability of error is m minus 1. Now, since all these probabilities are equiprobable and there are m minus 1 events. So, p m minus 1, that is m minus 1, because they are all equiprobable. So, this in our case would be given as m minus 1 p 2, 2 indicating binary comparison between any two, and that probability of error we have here, we given over here. So, that means m minus 1 times p 2, because there are m minus 1 such comparisons, this is the upper bound, that is probability of error is bounded by that. M minus 1 q function of whatever we have here is what we have used there, which can be further said to be less than m times, because we are ignoring 1 for large values of m. You may keep 1, but this helps us in finding some bounds, right. So, now what we do is we use the Chernoff bound for a q function. So, q of root over E s by n naught is less than or equal to e to the power of minus. So, basically q of x, we use this, is less than or equal to e to the power of minus x squared by 2. So, that is E s by 2 n naught, right. That is what we have from the Chernoff bound. So, then using this we simply replace over here. So, m e to the power of minus E s by 2. So, we replace this expression in this. So, m is 2 to the power of k, e to the power of E s is k times E b 2 n naught, right. E s is k times E b, because it is a signal energy, it is the bit energy multiplied by k bits per symbol is signal energy. So, what we have is this, we can say is further we have 2 to the power of k. So, we convert this to e to the power of, and this is the expansion that we have. So, we have this particular expansion in the numerator. So, from this what we can see is as k tends to infinity, as k becomes very, very large, that means m becomes very, very large, that means we are in the curve, we are going in this direction as m is increasing, right. So, as k becomes very, very large, p m tends to 0. So, again going back to this figure. So, you could also view it as m from 2 4 m, probability of error goes to 0, that is what we have. So, we can see from here also, right. So, from this union bound, now you could visualize what we explained intuitively a few minutes ago. So, but the condition is E b by n naught should be greater than this number. If it is not so, what do we have? We have a negative number inside, a negative number along with this would yield a positive number, that means the probability of error will start increasing. So, the probability of error will keep on decreasing subject to the condition that E b by n naught is greater than this, which is equal to 1.39 or roughly 1.42 dB. So, this tells that as long as SNR is greater than 1.4 dB, you can try to make Pm vanishingly small. And how will you do it? You will simply increase k, you keep increasing k over here, and then you could make arbitrarily small, that is you could make the probability of error almost become 0. That means, you could establish a very, very reliable channel without much complexity. But the question is, what is the penalty paid for achieving this particular result? So, as you increase k, what do we have? as we increase k, we keep on increasing the number of frequency bands. So, as we keep on increasing the number of frequency bands, we are tending towards using a very, very large amplitude. So, if bandwidth, as k tends to infinity, you are tending towards infinite bandwidth. So, what we have in this case is the probability of error is traded off with the bandwidth. That means, if I could produce huge amount of bandwidth, even the same constant transmit power, I could achieve significantly low probability of error. Now, if you contrast this to the PAM transmissions, what you would find is, given a finite bandwidth, that means Ts symbol duration, because bandwidth is inversely proportional to Ts, 1 upon Ts, it is equal to 1 upon Ts. Then if I have to reduce the probability of error, I have to keep increasing the power indefinitely. So, there probability of error or bit rate is exchanged with power. Here the same is exchanged with bandwidth, right. So, that is what we have a bandwidth error probability trade off in this case, right. However, one could guess that the bandwidth efficiency would be very less, right. So, continuing on this, there is a tighter bound than what we had just discussed. So, going into the details of the tighter bound is bit constrained at this particular point of time. So, we will use the result simply over here. If it permits, then we can provide you with the necessary steps at a later time, but I doubt that it is possible given the fixed number of lectures that is possible over here. Still, we will try to provide you with additional material which you may go through. So, a tighter bound is for EB by N naught less than for ln by 2. So, as of now, let us take that somebody has derived this and we are using this result. So, for lower SNR regime, I mean this approximation that we have used is not a very good approximation in the low SNR regime. This approximation is good for larger values of EB by N naught. So, for low SNR region, the probability of error can be upper bounded by this expression, where this condition is true only when EB by N naught is less than is greater than ln of 2. So, again I am stating that this result we are using from some other derivation using a tighter bound of the expansion. So, this tells us that as long as EB by N naught is greater than log natural logarithm of 2, which is 0.693, that means greater than minus 1.6 dB, you can keep increasing k. That means, you could make probability of error go to 0 as k increases indefinitely, but you have to maintain gamma b greater than minus 1.6 dB. So, what we have is that minus 1.6 dB is the minimum required SNR per bit to achieve an arbitrarily small probability of error. And remember, this is achieved by making bandwidth go towards infinity. So, with this we have analyzed the performance of a few digital modulation techniques in AWGN channel, but since we have done them separately, but although we have taken insights at appropriate stages of time, where we have seen how probability of error or bit rate are traded off with power and bandwidth in individual case, it is very important that we compare all of these in one single discussion or in a common platform. So, to discuss these things in a common platform, we require to understand, or at least use, if not completely understand, some important terminology in the domain of digital communications known as channel capacity. So, we will discuss the channel capacity at least somewhat quantitatively, but I do not know whether the time that we have will be able to do justice to that in this particular course. However, the particular discussion on channel capacity which is going to take place in the next lecture will be mainly on information basis, which will not be a regular part of evaluation. However, we will use the expression of channel capacity that we finally get for evaluation at the end of this particular course, but at least we should keep the notion of channel capacity, what is the meaning and why should we use it, and we will use that as a benchmark for comparing the performance of digital modulation techniques that we have seen so far in the upcoming lectures. Thank you.